Just so you know, this is what I look like. I'm going to turn the video off in a minute. I'm a trainer and I work for SNT, and we have a relationship with LINX, and we run IP, TCP IP network related courses which have a tie-in with LINX. So if you do need to get a LINX accredited qualification, then feel free to get in touch with us or through LINX, and we can get you on a course. Today, I'm going to just talk about BGP from a very introductory standard. I'm going to assume that really you know nothing about BGP, and I'm going to go through it in a way that really just talks about BGP and how BGP works. I'm not really going to address problems of peering, because as Holly will tell you at the end of this session, we're doing another session specifically aimed at more peering with BGP, and that's going to be in a couple of weeks. So today it's how BGP works, and I think that's all I need to say before I start. So I'm just going to stop my video. Now I'm going to share my screen, and you can see here that here's the title, and I've got a load of slides that I'm going to draw on. Everything that I draw today will be saved as a PDF, and I'll give it to Holly. And if she can make it available for distribution, that's fine. So if you need a copy of these slides, then get in touch with Holly and she can probably give you one of those. Right, off we go. Now, BGP. A lot of you, if you're networking people and you're looking for an introduction to BGP, you'll know the term IGP, which stands for Interior Gateway Protocol. And these are the routing protocols that we specifically use within autonomous systems. And they're relatively well understood, and you'll know the characteristics of IGPs are that they are very chatty, and they tend to tell everybody everything, and they'll auto-discover neighbors. So when you're running an IGP inside your corporation, all the routers tend to self-discover each other using some of these IGPs. Now, when we talk about IGPs, you're probably all shouting things like RIP and OSPF and maybe ISIS. And if you really love that thing from Cisco, EIGRP. So those are the way that routers exchange network information within an autonomous system. And the way that they work is that they will communicate information. So we've got network 10.1.1 over here, and say that we were to be running OSPF inside our corporate networks, then OSPF would send messages, and everybody would self-discover and auto-discover each other, and messages would flow all through the network. And then if we look at the point of view from router 1, how does router 1 actually find the best path to network 10.1.1? Well, it's just going to use OSPF link costs, and it's going to walk down each link. So it'll take a walk down that way, and it will add up all the costs, and it'll get 10, 11, 21, 22, 23 that way. And if we go this way, it'll add up the costs. It'll get 1, 10, 1. So the cost this way is 12. So which way is it going to go? It's going to go this way as the best path. And that's a very simple decision-making process. And it rests on one thing, and that is a cumulative path cost. So with these IGPs, one thing that the thing that they use to judge best path is they use a metric. And that metric is usually a single thing and is very simple to understand. If we think about BGP, well then BGP is the really truly the only example of what we call an exterior gateway protocol. So BGP is the only EGP, and BGP is the only routing protocol that would be used between these special things called autonomous systems. And with BGP, it is definitely not chatty. So the key thing to remember, it's not going to tell you everything it knows. If you go back to OSPF, OSPF tends to tell everything it knows to all its neighbors. Now, BGP is not chatty, and very much BGP only tells you what it wants to, what it wants you to know. So it's very configurable. And as for judging the metric, there is no single metric in BGP. Multiple metrics exist and can be taken into account when deciding the BGP best path. Now, what is an autonomous system? Well, an autonomous system, the classic definition of an autonomous system is simply a group of routers under single administrative control. So that will be something like an ISP, a corporation, or some kind of networking entity. So how are autonomous systems identified? Well, autonomous systems are identified through numbers. So if we just said, okay, we've got level 3, a transit provider, we've got the BBC, we've got Virgin Networks, and we've got Sky. Now, they will all have autonomous system numbers. So for the BBC, it is 2818. So they all have autonomous system numbers. And using those autonomous system numbers, they can establish BGP relationships with other autonomous systems, and it's through those BGP relationships that they can learn about networks that belong to other autonomous systems. Now, these autonomous system numbers, they can be, if you look at this table here, you see for you binary fans, that if we're going up to 65,000, then you know that they are 16 bits. So we do have some 16-bit autonomous system numbers, but then you can see that we've got these 32-bit autonomous system numbers as well, because they were running out, and so they expanded. So this is a possibly a 4-byte number. When we're thinking about BGP between autonomous systems, it's very much used to manipulate the flow of traffic. BGP is not chatty, and it doesn't tell everybody everything. It tells you what they want you to know to try and influence the way traffic flows into and out of their organization. With BGP, a lot of the time, money can be involved. So if I'm going to tell you about a network and you're going to send traffic to that network through me, why should I do that? So money can be involved when we are providing a traffic service through my network to get to another network. So let's think about who needs BGP. Well, a home user. Do I need BGP? Clearly not. Home users with their routers, they just have nice and simple default routes pointing to the internet, and then the provider's probably going to have a nice static route pointing to them. So there's no need for any BGP there. So let's go on and say, okay, well, you've got to remember about all these private networks. These are, of course, the RFC private networks. This would be RFC 1918. And these are the private networks used within organizations. And with BGP, you should never be advertising these, because with BGP, it's only concerned with public networks. So you have to remember to use filtering and check that you don't advertise these kinds of networks to the world. If we look at this situation, then we do see we've got an ISP connected to a corporation, and that corporation has maybe got some web servers down here. And those web servers do have public IP addresses. And if they've got public IP addresses, you might think that, okay, we will need to have some kind of BGP relationship to advertise those public IP addresses to the world. Well, in fact, in this case, you don't. Why not? Because the ISP is your only way to get to the outside world. So those public IP addresses will be known by the ISP, and they've probably provided them to you. And so the ISP can simply have a static route pointing to your public addresses, and you can simply have your normal default route pointing to the outside world. So we don't need BGP here, even though we do have some public addresses. BGP is really when you want to manipulate traffic. And if you're trying to manipulate traffic, then that means you want it to go one way in preference to another way. So that means you definitely need to have multiple gateways to the internet, or multiple gateways to anything. And if you've got multiple gateways and you want to influence which way the traffic is going through those gateways, then you need BGP. If we look at this example here. So here we've got an ISP, and it's got an autonomous system number there. There is a corporation who is a customer of that particular ISP, and it has its own autonomous system number here. If that corporation needs some public IP addresses, then where's it going to get those public IP addresses from? Because it's completely hidden behind the ISP, it's probably going to get those public IP addresses from the ISP. Now, the ISP has been given, for example, a /16. And that is that ISP's public IP block. If it's been given a /16, it might take some of that IP block and allocate it to the customer and say, okay, I'll give you a /23. So that /23 is allocated as network A to customer 1. Now, customer 1 can take that network A and further subnet it into two 24s. We've got network A1 and network A2, you can see here down at the bottom. Now, the customer now has multiple gateways to the ISP. And you can see that network A1, it might be nicer if the traffic were to come down here to get to network A1 and to come down here to get to network A2. So we're now in the position of wanting to manipulate traffic flow. So how are we going to do that? Well, I've told you that if you've got multiple gateways and you want to manipulate traffic flow, you use BGP. So if we come here, so we've got a BGP relationship from the customer to the ISP. And if we imagine that we insert a router in the ISP. So we've got a router there in the ISP, and we can label those routers there, router 1 and router 2. So down here, we could have router 1 and router 2. So this is router 1. And this is router 2. Now, if you advertise network A1 up into the ISP, but you advertise it through this BGP session, so you're getting network A1 advertised up there. And like similarly, you're going to get network A2 advertised up there. That means that from the ISP's routing point of view, it'll have entries in its routing table. Now, the entries that it'll have in its routing table are going to be network A1/24 via router 1, network A2/24 via router 2, which is exactly what we had here. So we're advertising the /24s. So that means that traffic for this /24 is going to go this way, and traffic for that 24 is going to go that way. But what if this router here, router 1, fails? Well, if router 1 fails, we'd like the traffic that was going that way to be diverted to go this way, because we've had some kind of network failure. So how, if we think about what we've advertised, how is that going to happen? Because we only advertised network A1 up through this link. Well, clearly the answer is, when we advertise, we do in fact advertise network A1 up that link, network A2 up this link, and they are /24s, but we also advertise the complete summary of the two networks up each link as well. So we'll get network A advertised up each link as well, and that is an aggregation of both of the 24s. So when we look at the routing table, we do see that we have the /24s going to the specific routers, but we have a /23 covering all of the network going to both routers. So that if for some reason this route drops out of the table due to the failure of router 1, any traffic going to the network A1/24 gets picked up by the aggregation to 23, and because router 1 is down, it will go via router 2, and so we've picked up the traffic. And so it seamlessly, if there is a failure, we can get the traffic redirected through the other gateway, because when we did the advertising using BGP, we advertised specific routes, but we also advertised the aggregate route in case the other side fails. So that's how to manipulate traffic flow through using BGP. You advertise what you want on each link, and you think about it and you think, well, what's going to happen when things fail? Where do I want the traffic to flow? BGP is all about the manipulation of traffic flow. Now, when we think about those IGPs that we talked about earlier, so if we just flip back and we think about the IGPs, then when you configure these IGPs, they, if you're very old and RIP, can communicate using the broadcasts, and all of them can communicate using multicasts. So you see that this is how they auto-discover, because they just shout out to the world and say hello. Now BGP, we've said, is not chatty. So with BGP, when you set it up, BGP is connection oriented. So with BGP, you do have to manually configure it. So BGP can be manually configured. There are automated systems, but generally you have to say and specify who you want to talk to. So your neighbor's identity, and your neighbor's identity will often be an IP address. Your neighbor's identity is part of the configuration. So BGP doesn't just shout out and find neighbors. Also with BGP, the thing that you should know is that it works over TCP. So if it works over TCP, you will know that TCP is a connection-oriented protocol. So at the beginning of any BGP relationship, you must first set up the TCP connection. So if we look at this diagram here, you see two autonomous systems. Between them is a network, 195.66.24, and we've got two IP addresses on the end of that link. And you can see that if we look over here, that this IP address is specifically mentioned as part of the configuration on this autonomous system numbers router, and that this autonomous system number is also explicitly mentioned when you configure your neighbor. And if you do that on both sides, then TCP will contact, and so you will get your traditional TCP, which will be one message, your TCP SYN, then you get your SYN-ACK, and then you get your ACK, and so you will have a TCP three-way handshake at the beginning of the BGP relationship. So we'll get our traditional SYN, SYN-ACK, and ACK. So once that's happened, you can now have your BGP relationship. So we've said that BGP sits on top of TCP. It's connection oriented. You have to explicitly configure your neighbor's autonomous system number and IP address. And then there are some timers. There's a keep alive timer and a hold timer. So if I don't hear anything from you for a certain amount of time, I'll just abandon the connection and believe you to have kind of died. So we've got that BGP connection going. In terms of messages, then you will have a BGP message, and that BGP message will be transported inside of a TCP message. So we're going to have a TCP header, and you know the most important thing there is the source and destination port numbers. Now for BGP, what is the port number? Well, the port number is 179. So I could be sending to 179, hoping to reach the BGP process at the other end of the link, and the source port can just be one of those private ports that's dynamically allocated. That's the TCP. Once we've got the TCP, then clearly that's going to be wrapped inside of IP, and we're going to have IP addresses in the IP header. So there's the IP header, and we will have the source and destination IP addresses, and then all of that is probably going to go down, you know, often it go down an Ethernet link, and you'll get an Ethernet header. So here is some Ethernet wrapping it all up, sending it down the link. All of that would be a nice BGP message with its encapsulation. Now, when we're talking about BGP messages, just to tell you again that the port number for BGP is port number 179. Now, when we're talking about BGP, there were two ways that you can do BGP. There is what you might call, you know, the eBGP. So we've got eBGP, which is external BGP. So this is external BGP, and external BGP is between different autonomous system numbers. There is the capability to do iBGP. Now this is internal BGP, and this is within the same autonomous system number. Now, when we think about BGP messages, which messages are there? Well, like all connections, if I'm going to open up a connection with you, all connection-oriented protocols, they have different message types. And when we're talking about the message types for BGP, the first message type is going to be an open. That's you trying to connect to the other end, trying to get to open up a BGP session. After that, we want to keep that session going. So we have a keep alives. And then how do I actually get to you information about networks? Well, there are BGP updates. And it's the updates. Inside the update, one of the key things that you're going to find is the NLRI. That stands for Network Layer Reachability Information, which in yours and my minds just means IP prefix with a subnet mask. So inside those updates, you get these NLRIs, and they give the prefixes. Inside the updates, you also have descriptions of attributes that belong to that network, and we'll talk about those later. Another kind of message that BGP sends is a notification. And a notification is simply an error. So it's a BGP error, such as something's wrong, the autonomous system numbers don't match, something like that. And then the last one is a route refresh. Now, route refresh, it was a later kind of message that they came up with, and that's very useful in, you're basically saying to the other side, oh, just send me the routes again. and it means that we don't have to completely close down the BGP session and open it up again in order to get all the routes sent again because we want to refresh our tables. And lo and behold, what you have here, you clearly have a Wireshark analysis of the opening of a BGP session. And when you look in there, you do see our beautiful three-way handshake at the beginning. So here is the TCP three-way handshake. And you do see that I didn't lie. And the port number 179 for BGP. So we're contacting BGP at the other end. We're trying to set up a connection. And then I use that TCP connection to send my open message. I've got a keep alive in there. And then you can see we've got some updates going through as well. So there is the establishment of a BGP connection. If we do look at that open message, which is right at the beginning, then this is what you're going to see. And clearly, if you are trying to set up a BGP session with another router, you will have to, in the open message, declare your autonomous system number and your BGP identifier. So that's a bit like an OSPF identifier. It identifies you in that BGP. And clearly, if we go back to this slide here, if any of the configuration doesn't match on the other end, if you declare your autonomous system number in the open message and the other end's autonomous system number that it's configured to have a relationship is different, then you'll get a notification message and a BGP error. So that's the BGP open message. One thing I'll just point out is they do tell each other the capabilities. And one is I can support 4-octet AS numbers. Well, it'd be a sad old router that didn't support 4-octet AS numbers in the modern world, but who knows, you might find one. Other thing to notice is we do have the BGP version number, and the current version of BGP is 4. It would be an odd thing to find a BGP router that didn't do version 4. So we've got our relationship going. When you set up the connection, just like TCP connections, they can go through various stages. Now, I don't want you to get obsessed about this, but these are the BGP Neighbor States. So you might look at a table of BGP neighbors, and what you want to see when you look at the table of BGP neighbors, what you want to see is that they are established. And that means the BGP relationship is up and happy. What you don't want to see is that the relationship, the state of the neighbor is idle, because that means that, well, nothing's going on. We're trying to establish TCP. And then you've got some more intermediate stages: connect, active, open sent, open confirm. And really what you're looking for is established, and you're not looking for any of the others. But some of the names do help you to understand what's going on. And here is, now this is a bit small, let me just make it a bit bigger for you. Here you can see this is a bit of debugging of a router, and you can see that we've changed state from idle to active, and then we've gone from active to open sent, and in there you can see we do end up at what we want, and what we wanted was to be established. And then you get a message, BGP adjacency change, the neighbor is up, and that's exactly what we want. Going back to those updates, because that's really the meat of BGP. It's the updates because we're trying to communicate to the other side some network information. What can you have in an update? Well, the first thing I'd like you to realize is that you can have multiple updates in a single BGP message. So updates, you can have multiple updates inside a single BGP message. And you can then give with notice of withdrawn routes. So you can say, hey, that route that I told you before, take it away, no longer valid. Or you can announce to them new routes that are valid. And here is that network layer reachability information, which we said was really just a prefix. So there it is. And you can announce multiple prefixes for a set of attributes. We're going to talk about attributes in a second. Here is one from our friendly Wireshark. What you see in there, well, you see, of course, that one of the port numbers is going to be 179. And you do see that this is an update. So this is a BGP update message going through. You can see, in fact, in this, I've got multiple updates going inside a single communication, multiple updates inside a single communication. And this update here is saying, okay, I'd like to tell you about this IP prefix. So it is this router here telling this router here that you can reach this IP prefix, can be reached through this next hop. So what's it saying? It's saying, from a BGP point of view, if you want to reach this network, send the traffic to this IP address. So that's the path attribute. For that NLRI, it's saying send the traffic to this IP address, which you can see is the same IP address as the sender of this BGP message. Good. Now, these attributes, and I don't want to get too obsessed by attributes, but these attributes are described as well-known or optional, and some are mandatory, some are discretionary, which means optional, and there are different attributes, and the attributes give some characteristic of that route. So the route to that prefix is described using attributes. And one of the attributes that must be there is, where do we send the traffic? You do see another attribute called AS path, and that will list all the AS numbers on the way to reaching that IP prefix. Now, these attributes, here's a table. We all love a table. Here are some attributes, and you can see there are 3 mandatory attributes that must always be there, and that is next hop, AS path, and origin. We have some that are discretionary, so they don't need to be there, they're optional. Local preference, atomic aggregate, and you can see, according to what the attribute is, what is the behavior of BGP? Well, if the next hop attribute is there, eBGP passes on the next hop attribute, but replaces the IP address with its own IP address. So an eBGP router always puts itself as the next hop when it is advertising routes. And that's crucially different to iBGP, which does not. and we'll talk about the problems that can have later. So those are attributes. There's some more attributes here that we can describe a route with. And one of the most useful that I want you to just take a little note of is this: communities. And what are communities? Well, communities are just, you can think of them as tags or labels for routes. And we'll show an example of how communities are used later on. So here I'm on a router and I've just done a show IP BGP summary. Everybody will go, oh, that's a Cisco router. And you see I do have a neighbor at 197.121. So here is my BGP neighbor. And they have sent me no prefixes. But then what I've done is I've gone to the neighbor, I've told them to advertise something, and now you can see that that neighbor is now advertising one prefix it has sent to me. Notice that the BGP table has version numbers. Here, the BGP table was version number 1. There was nothing in it. They did some updating. Now it's version number 3. So here is that update. We've got 2222 being advertised from 197.122 to 197.121. It's advertising the 22222 network. So there are some attributes. Now, if we look at a show IP route, you can see here in this show IP route, we have now a BGP learned route. There it is. And that was the route that was advertised during this update here. So we've got a BGP update. It's advertising this prefix. And that came from this IP address, 197.122. If we look here, it's now in the major routing table. 197.122 is where we should go to send the traffic. And all routers running BGP also have a route BGP table. So this here is the BGP table. And you can see that the next hop, 197.122, belongs to 2222. And there is the AS path that we use to get to that 2222. We only go through one AS number, 65522. How do we get there? We send the traffic to that next hop. And you can see these symbols at the beginning in the BGP table. And the key symbol to look at is this one here. This is the best BGP route we have to go to that network. So this is the one that gets offered up into the table. So those are attributes. Now, a little more. When we look at this here, this is the BGP table. And this is a list of all the routes we've learned via BGP. And there are some status codes, and there are some origin codes. Now, these origin codes, well, you can see that for all of these routes, the origin is IGP. Now, this origin here, EGP, you will never see. So if I'm going to talk about these origin codes, EGP, you never see it. If you see an origin code of incomplete, it means that route got into BGP, probably through redistribution. If you see an origin code of IGP, it really means that they used the network command during configuration to inject that network into the BGP process and get it advertised out. And here is that origin there. So there is origin, one of the mandatory path attributes, and you will always see it. You see next hop, you see AS path, and you see the NLRI for the prefix. If we think about a router running BGP, so here is router 1. Now router 1, for forwarding its normal IP traffic, will have a routing table. That's called your rib, or the rib. Now, if we have BGP relationships, that means BGP updates will be coming in. And those BGP updates go into a BGP table of updates coming in. So this is called an adjacency rib in. So for that relationship with the other router, let's call it router 2. For that relationship with router 2, all the updates carrying prefixes, those updates will go into the BGP table adjacency rib in, maintained by BGP. So the prefixes that arrive in those updates go into a table. Now we may apply filters to that table so we can filter what comes into us. And by using filters, some of those prefixes can just be put directly in the bin. So we can bin some of them because we don't want them. Others can be sent into the BGP routing table. So then we have routes in the BGP routing table, and BGP then needs to decide for a particular prefix which is the best path. So BGP will then go, okay, that is the best path to that particular prefix. I have many options to get to that prefix, but this one is judged to be the best. Now, the best path is then offered up into the routing table, and the routing table might accept that and go, okay, I'm going to use your BGP path to that particular prefix. And that is the one that will be actively used to forward traffic. Now, even though it's the best path according to the BGP table, it may not make it into the routing table if there's something with a more preferable administrative distance, such as a static route. So just because it's the BGP best path doesn't mean it's going to be used. Now, it's only the best path that will then be advertised out into the BGP out table. So we then have the best paths that are put in the BGP adjacency out table. So we've got BGP in, we've got BGP out. So this is going to be the adjacency rib out that relates to router 3, and it will only be the best paths that are advertised out, and for those to be advertised, that network needs to be in the routing table in some way. So that's how BGP works. BGP updates come in, we learn prefixes, they go into the in table, we might filter them, some might go into the bin, some of them get into the main BGP table. So this is our BGP table. Of those, BGP decides which are the best paths. They're offered to the routing table, and they will be advertised out to our neighbors. There are some timers involved with BGP, such as the hold time and the keep alive timer. Now, keep alive timers suggested 1/3 of the hold time. The default, if you look at the RFC for BGP, the default hold is 90 seconds. So they're suggesting a keep alive timer of 30 seconds. Depends on your implementation, and you can play with that. One thing that's very interesting, well, to me, is that there are some other timers, and there is this MRAI, minimum route advertisement interval timer. So if I advertise a prefix to you, I have to wait a minimum time before I can change that. And so they suggest it should be 30 seconds. So if I tell you about a route, I have to wait 30 seconds before I change that route to withdraw it or update it. An academic study was done, and it was found that most people actually turn this off because it speeds up convergence so that all the routers become up to date quicker if you make that timer very small or non-existent. And we all like a quick converging network. Good. So I've really talked about what BGP is. I've talked about how BGP works, the relationships, prefixes. I've talked about attributes, and I think we've come to a natural break. And after the break, I'm going to talk about how BGP makes decisions, and we'll look at the difference between external BGP and IBGP. So welcome back, everybody. Let me share my screen. So before the break, we talked about BGP needs a TCP connection, different types of messages, opens, notifications, keep alives, updates. It's updates that are meet, because that's how we're advertising prefixes to the outside world or to our ASN neighbors. And I did tell you that BGP does not use a single metric. So let's go on and talk about how BGP makes decisions. One of the things you've got to do is prevent BGP routing loops. And it's quite easy to do. If we look at this diagram here, you can see we've got two ISPs. We have a third ASN down below. And simply, if we have BGP relationships between these autonomous systems, and you can see if we were to create some kind of loop, and that ISP1 was advertising network 2. So when network 2 is advertised that way, then we did say there was an attribute called AS path. So here is that attribute, AS path, and it is a mandatory attribute. So when you do advertise a network, you need to put on AS path, and AS path in this case would be 64501. So it would say 64501. When that update got into ISP2, it might advertise network 2 down to ASN 64508. It always will if it's doing eBGP. We did say earlier for eBGP, for the next hop attribute. So if we're doing eBGP, the next hop attribute, always replace with your own IP address. So going back here, as network 2 gets advertised down, they will replace the next hop as its own IP address here, and it will add on its own AS number. So the AS path list now becomes 64501, but added on to the front will be 64502. So that is AS path. If we were to advertise network 2 back to the original, so if we now advertise network 2 back to the original, we need to add ourselves on to the AS path. AS path was originally 64501, followed by 64502. And now we add on our own, which is 64508, 64508. So this is our AS path. And when that comes in, ISP1 sees its own autonomous system number in the path, and so it would reject this as I see my own AS number in the path. And that's how BGP stops routing loops. If you see your own AS number in the path, you drop it as a routing loop. Now, we did just say that eBGP is between autonomous systems. If we're going to send the BGP through this autonomous system here to come out at the other side, that must be iBGP. So we have eBGP between autonomous systems, but within an autonomous system, we would be using iBGP. And that's how we prevent routing loops. Now let's look at how BGP decides on best path. Well, to decide on best path, we need to think about this situation. So say ISP2 advertises network 1. So we'll imagine there are BGP relationships like that. We'll imagine there's a bit of iBGP going through there, and network 1 is being advertised up there. It will be advertised, and the AS path up there would be simply 64502. Network 1 can be advertised in this direction. Of course, the AS path is going to be the same, a single AS number of 64502. If network 1 then traverses this autonomous system and is advertised out the other end, network 1 will have an AS path, and that AS path is now going to have two AS numbers. We're going to have the original 64502, and we're going to have the one that it's just been advertised by, 64508. Now, when those get into ISP1, what does ISP1 do? It looks for the shortest AS path. Now, the shortest AS path is that one. So there's the shortest AS path. So this is the advertisement that would end up in our routing tables. And so traffic would be flowing that way because of the shortest AS path advertised. Now, so that means that the first way that BGP makes decisions, and so here is the update. So we've got a BGP update. Here is the network that we're advertising, and here is the AS path attribute for that network. And you can see here we've got 2 AS numbers, and that would be taken into account while making the decision. So our traffic is going to flow. So from the decision-making process, we do take into account the shortest AS path. And that will be the third thing that we look at, the shortest AS path. So what else can we look at when we are thinking about traffic flow? So at the moment, our traffic is going to flow this way because of the shortest AS path. What else can BGP look at? Okay, let's look at this situation. So we've now got the situation of the network being advertised. So the network is being advertised in here. So we have the network being advertised in there. We have the network being advertised to there. It's going through using iBGP, and it's being advertised here. Now, what we can do is, I did say that we can use filtering on routes that come in. So what we could do, and we can set policy. So when that network is advertised into us, we can capture it using a filter. So a filter implements what we would call our routing policy. So when the network is advertised in, a filter picks it up, and it then says on that route, we wish to set local preference to be 100. When the network is advertised in from ASN 64508, we can tell BGP to set local preference to 120. So that means that when that route gets to this router here, so if we call this router 1, it now has 2 routes available going to that network. It can go this way with a local preference of 100, or it can go this way with a local preference of 120. Which one wins? Well, highest local preference preferred. So when we look at our decision-making process, then our decision-making process now includes local preference. And so local preference is taken into account. We're looking for the highest, but we always consider local preference before we look at the AS path. So if there is a local preference and they are different between 2 options, we don't look at the shortest AS path. So if I go back to this situation here, we do have 2 options, local preference 100, local preference 120, to the same network, we will always choose the highest local preference. Our decision has then been made, and we do not even look at the length of the AS path. So in this situation, our traffic is going to flow this direction. And why does it flow that direction? Because when the route was advertised into us, we set a local preference. That local preference is an attribute. So if we come back here, that local preference is an attribute. Let's see if I can see it anywhere here. No, it's not there, but here it is. Local preference. It's not mandatory, it's an optional attribute. And it will only be passed on inside your autonomous system. So all routers inside your autonomous system will see the local preference. That means all routers inside the autonomous system will prefer to send the traffic in the direction with the highest local preference, which means that in this situation, we're sending traffic through that other AS. So it's actually going in a longer path. But that was our decision when we set the routing policy on our incoming routers. We decided to set a filter which caught the route, set a local preference, and that means we've made the decision to prefer the bottom route instead of the top route. And you can see that local preference is actually influencing traffic leaving our autonomous system. So when we're talking about local preference, it influences traffic leaving. So it influences outgoing traffic. And if we make a decision on local preference, we don't even take into account autonomous system path. If we look at this situation here, autonomous system number 64501 is declaring to the world its routing policy. So routing policy is you implementing actions to manipulate traffic. So here, this ASN 64501 is declaring to the world, okay, if when you send us a prefix, if you put a label, now we talked about communities earlier, they're just a label. So if you simply label your prefix with one of these labels, we will set these local preferences. So what we can do, we have an autonomous system with two networks. We can advertise both networks using BGP. So we've got BGP relationships. We can advertise both networks. So I can say, okay, network A, I will advertise up there. Network B, I will advertise up there. I will advertise both networks up this side, network A and network B. Now, clearly, we would prefer the traffic for network B to come this way. So how do we do that? Well, the default local preference is 100. So here, they're giving you local preferences that are lower. So if I know that the default local preference is 100, what I can do is when the BGP advertises network B internally, I know that the default will be a local preference of 100. So we will get network B will get there and it will have a local preference of 100. Now that's the default. But what about the other side? When network B is advertised to here, what will be the local preference? Well, by default, the local preference would be 100. So that means there's no decision made at local preference. They'll look at AS paths and other things to make a decision. But what we can do is we can say, okay, I don't want that. I want, when network B reaches the internal router, the advertisement, I want the local preference to actually be 80. So if I can make the local preference 80 on this route, but 100 on this route, I can then get the traffic to network B to flow in this direction. Now, how do I influence that? They've told me that you can set the local preference on routes just by adding the community label. So I will add 64501. So I'm going to take the community. I'm going to, when I advertise network B, I'm going to label that prefix with the community, that is 64501 80. So that community label is attached to that prefix. When it enters their AS, they will set the local preference on network B to 80. Internal router now has the same network with two preferences. It chooses the highest, and we've influenced the traffic. Clearly, we're going to do the same with A. So across here, we can attach the community 64501 80, which will make it so that when the prefix for network A reaches here, they set the local preference to 80. Here, we won't do anything. So when network A gets here, it'll have a default local preference of 100. This router, which way is it going to send traffic to network A? It's clearly going to send traffic to network A this way because it has the higher local preference. So this demonstrates to you two things. It demonstrates that you can tell the outside world how they can influence traffic flow. So this autonomous system number at the top is allowing its customers to set the local preference they prefer to get traffic to come in one gateway rather than the other. And this is by declaring your routing policy to the outside world. Good, so that's BGP decision making. Local preference, shortest AS path. The other thing that you can do if you want to influence traffic is you can do a sneaky thing called AS path prepending. So if we look here down here, we've got 64508. It's advertising network A. Well, the AS path would be 64508 when it gets advertised in there. If it's going to be advertised up there, the path would then be 64508 with 64502 added on. It would be the same the other direction, 64508, and when it got there, the path would be 64508 with added on 64503. This AS number here could sneakily add on its own AS number once more. And so you can see you've got duplication. And here, this is called AS path prepending. And what I'm doing is I'm trying to make ASN 64501, I'm trying to force them to send the traffic this way because I'm making the AS path longer. So you can influence traffic coming into you and make it go another direction by advertising a very unattractive path by putting on your AS number a number of times. Clearly, this can easily be spotted by your neighbor and they can strip it off and say, please don't do that. So there's the BGP decision-making process. What else do we have to consider? Well, the next thing we have to consider is something called weight. Now, with weight, this is purely for the local router only. So routes in from router 1, we can set a weight on them. So if we set a weight on them, if we set the weight on the incoming to 100, if for the others, we can set the weight on these incoming routes to 200, we do in fact prefer a higher weight. So from this router's point of view, when the routes come in from router 2, they set a weight of 200, so we'll always prefer routes from router 2. So from this router's point of view, it sends traffic that way. Now you're influencing traffic going out of your router, but one thing to be very careful about on weights is that routers behind, weight is not an attribute. Weight is merely a local structure. And so that weight is not communicated to any other routers. So the router behind may be sending traffic this way. So you have to be careful and realize that weights are only, they're only active on the local router. No other routers see the weights because they're not attributes, they can't be communicated. So we've got weight, we've got local preference. Now with weight, you want the highest, local preference is the highest, shortest AS path, and there's one other thing I want to talk about. If you've looked at all of those and they're all the same, so you haven't been able to make a decision, all the weights are the same, all the preferences are the same, all the AS paths are the same length, what can then come into effect? Well, what can come into effect then is something called the MED. And the MED is multi-exit discriminator. So what happens here is that when you advertise routes out, you can set the MED. So if you advertise routes out and you set the MED to 100, and when you advertise the routes out here, you set the MED to 200. So if you're advertising out network A here with a MED of 100, when you're advertising out network A here with a MED of 200, which one is preferred? It will be the lowest MED. So you are telling this autonomous system number, please prefer this path. Now you only use MEDs when you have multiple gateways to the same autonomous system number. If you advertise out here a MED of 300, it has no effect because this autonomous system number only has one exit to you. So this autonomous system will always send traffic down here if it's going to that network, because it doesn't have multiple gateways into you. So it doesn't have multiple exits. So there you go. That's how BGP makes its decisions. It looks at the weight on the local router. If they're the same, it looks at the local preferences set on the routes. If they're the same, it looks at the AS paths. If they're the same, it looks at the MEDs. And if they're the same, it takes in things like neighbor numbers. This is actually a list from Cisco. This is a list of BGP attributes that it takes into account when making decisions. They can be long and involved, these decision-making processes, but it's the ones that are higher up that have the greatest influence. So if you think of the decision being made in this order, if you're setting meds and local preferences are also being set, then the meds really won't be taken into account. So if you really want to influence traffic, then local preference is probably the easiest way. And you can, as I've said, you can declare to the world, helpfully, you can tell the world about the local preferences by declaring your routing policy. And this allows the outside world to influence traffic inside of you, because when they advertise routes into you, they can attach labels, and you said, okay, you attach the label, we'll set the preference, and you can now decide which way the traffic is come. BGP is all about manipulation of traffic. So we've talked about eBGP. Let's just have a quick talk about iBGP, because it operates in a slightly different way. If you look at this diagram, then you can see that we have few autonomous systems there. If we look from the point of view of autonomous system 64501, let's imagine there is a BGP relationship. And so prefixes are being advertised into us. So they're advertising the 195.66.224 prefix. They're using BGP. So when that comes in, here it is. So this is going to be advertised. And that will go into our BGP table. And I'm just going to have to bring that to the front. There we go. Now in the BGP table, there's the prefix, and the next hop is going to be 195.66.2251. So the next hop is clearly going to be this here. Will be the next hop if we want to reach this network. Now, next hop is an attribute. We did see earlier, next hop is an attribute, and here it is. There's the prefix being advertised in BGP, and there is the next hop. And we've got an AS path there as well. So going back, we've received that update in our BGP table. That's what goes in, a prefix with a next hop. We offer that up to the routing table, and the routing table will actually take that and we'll stick it in the routing table as an official BGP route. And so from router 2, we can now direct traffic to that network. So we do want to somehow be able to advertise that prefix internally and out the other side to hopefully eventually get to router 5. So if we look at that, we're now going to have to do a bit of internal BGP. So if we do some internal BGP, and so let's go internal, and we can advertise that route up to router 3. So if we advertise that router up to that prefix up to router 3, then the BGP table is this. There's the prefix. And the next hop is 195.66.225.1. So the next hop is actually still over here. So this is the next hop that's being advertised to router 3. But if you look in router 3's routing table, it only has 2 directly connected networks. So it cannot find that next hop. So that means that that next hop is unreachable from the point of view of router 3. Next hop unreachable means prefix can't be used. Because how can I forward to a next hop? So that route does not make it into the routing table. So router 3 does not have an entry for 195.66.2240 because the BGP next hop is unknown to this router. Now the question you might say to, well, why didn't router 2 advertise its own IP address as the next hop? Because we did say earlier that with next hop, eBGP automatically makes the next hop itself. But the default for iBGP is you pass on the next hop, you don't change it. So when we come back here, when this router passed on, it did not change the next hop to be its own IP address. So we can actually configure that. We can configure the router to use next hop self. So if we're using next hop self, when it passes on that route, the next hop self will be its own 2261. Now, because 2261 is the next hop, and 226.0/30 is in the routing table, that means that the next hop is reachable. And so we can use that route. So that means that that route will actually go into the routing table. And it will go in as a BGP route. So now router 3 can send traffic to that network because it can reach the next hop, who will then send it on. So in the previous case, we couldn't get traffic from router 3 because the next hop was unknown. By setting next hop self in the iBGP, router 3 now gets to use that route. So router 3 can now forward traffic to this network. And that's very nice. So if we think what happens next, we want that route using iBGP, we want to get that route to router 4 using iBGP. Now there is a problem with iBGP, and that problem is you have this thing called BGP split horizon. And this applies to iBGP. Anything that you learn, you will never tell anybody else. So even though you have learned using IBGP, you have learned about the 195.66.224 network. Because you're using IBGP, you're never allowed to forward that information on this. So that route will never reach router 4 because of split horizon. So how do we get around this? Well, the way we're going to get around this is we're going to set up an IBGP relationship between router 2 and router 4 so that router 2 can directly send that update to router 4. Now, there is the tendency here to think, oh, does that need another link? Well, no, it doesn't need another link, because don't forget, BGP operates over TCP. So router 2 can merely open up a TCP connection with this IP address on router 4, and using that multi-hop TCP connection, it can send BGP updates directly from router 2 to router 4 using a multi-hop TCP connection. So as long as router 2 knows how to reach this IP address, it can contact it using TCP. And you can see that router 2 in its routing table does have the 195.66.226 in there, so it can reach it using TCP, so it can set up a long distance IBGP relationship, and now it can send that directly. So router 3 learns about the network. Router 4 will also learn about that network. And that means IBGP has succeeded, even though there is split horizon. And split horizon means you cannot forward BGP information to another IBGP neighbor. So that means you must have an IBGP relationship with every other router. So this means that if you are using IBGP, you do need full mesh relationships with all other IBGP routers. Good. So that's an explanation of IBGP. Now, with IBGP, if you are having these internal full mesh relationships, if you look at it, it means that you need an IBGP relationship there, 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 there. And this router needs relationships there, there, there. And this needs relationships there, there. And you can see all of a sudden, we've got a lot of IBGP relationships going on. If we're to use full mesh IBGP. So what we do have is we use these things called route reflectors. And with route reflectors, you have a single relationship with the route reflector. And that means that if a BGP update goes into the route reflector, it will reflect that update to all the other IBGP routers. And so you don't have to have this huge full mesh maintaining lots of relationships. That's the use of route reflectors inside networks. They're used to cut down the number of IBGP relationships. Good. And there we've come to the end of our presentation. The one thing I will add just before we go is that we've talked about BGP, and we've talked about BGP communicating IP version 4 address prefixes. BGP is very scalable, very extendable. And so you can, these are these BGP address family indicators. So BGP can carry many different kinds of addresses. So BGP can carry IP version 4 addresses. BGP can carry IP version 6 addresses. And within those families, there are subfamilies. So you can have IP version 4 unicast addresses. You can have IP version 4 MPLS VPNs. You could have IP version 6 MPLS VPNs. So BGP has been designed to be extendable, and you can they've extended it on not only for IP version 4 but for IP version 6. It's used in MPLS, it's used in MPLS VPNs. BGP is becoming the general workhorse for distributing any kind of network routing decision-making information. So I'm going to stop there. We've had a jolly good talk about BGP. I hope you're still there, and I will hand it back to Holly. Do we have any burning questions, Holly?
Hi, Rob. Yes, we do. And we have a couple. So just a quick reminder to anyone still on the webinar, if you do have any questions for Rob, just pop them in the Q&A and we can get those answered for you. So I'm going to try and read this out exactly how it says, Rob, so maybe you can kind of defuzzle it. So it serves keep alive BGP message to let he know the other side, ASN, to kill the BGP session. Does that make any sense?
Yes, so BGP keep alive. They're sent periodically. So if the default is every 30 seconds and my hold timer is 90 seconds, if I don't hear from you for 90 seconds, that means that in my eyes, you are dead, and I will kill the BGP session with you. I will bring it down and the session dies. Yes. So if I am using you as a next hop on any reachability information, all those routes will die as well, because I can't reach you anymore and your next hop has died. So yes, the BGP session goes down if the keep alive stop. But if the keep alives keep coming in every 30 seconds, then I know you're alive, even though you're not sending me updates, because everything is hopefully very stable. But I know you're still alive. I know you're still a valid next hop. And so, yes, keep sending the keep alives and our friendship lives forever.
That's great news. So another question from David. Can we add whole BGP tables into routers' routing lists and RIB? Would choose the best route, or we have to set best static routes and add to the routing list?
Okay, so from that, let me just kill that and let me just come back to my presentation. And we did, so this is related to when we talked about the BGP tables here. Now, so when you have a list of paths in the BGP table, BGP itself will choose the best path. And it will only advertise that best path out to the world if the network is in the routing table. You cannot force routes. You cannot say to BGP, oh, I just want you to advertise everything you know. It will only advertise out the best paths. So if you want to advertise something out to the world, you have to make sure BGP knows about it. And you have to make sure that that network is actually in your routing table also. So if you do want to force BGP to advertise something to the world, in the case of kind of BGP kind of route hijacking, where you're going to say to the world, oh, you can get to that network through me, even though you don't own that network, how would you get it into the BGP table? Well, you could just stick a static route to the null interface in your routing table. That puts the network into the routing table. So that means that BGP would be allowed to advertise it. How do you get it into BGP? Well, you just use the network command on the router using that prefix. And because it was in the table, it would go in the BGP table, and then you could get it advertised out as a best pal. You can't really say to BGP, advertise everything you know out. Because if you imagine that, all the BGP tables would be full of all kinds of stuff. And really, I don't want to be advertising to my neighbor suboptimal paths. I just want to advertise to my neighbor the best path, because that's a nice thing to do. I don't want to swell their BGP tables with information that's not really relevant, because they're only going to be interested in surely the best path. So I hope that helps and answers your question.